this is a couple of simple related rates examples. Related rates are is the last section in the chapter. It is fair game for Friday's test. Example 1, we have a circle. I can put a circle in here. Circle. So we have a circle, and it grows at a steady rate. And the question will be, how does the area vary? Okay, so a circle is growing. So that its radius increases at a rate, that should be a Q right there, that's a derivative, of 3 centimeters per second. So again, small circle, and then grows. If I can make my circle grow anymore. Okay, so the circle grows at a rate of 3 centimeters per second. Let's get this out of there. Okay, so we have a circle, and it is growing at a rate. Here's the question. How fast is the area increasing when, or how about at t is equal to 10 seconds? Okay, so all rate problems start with the geometry equation. The geometry for the area of a circle is the area is pi r squared. You would be expected to know that. Area is a function of time. Area depends on time, and so does radius. They're both functions of time. So we differentiate both sides of this equation with respect to time. Time is our independent variable. So here's the calculus. The derivative of area with respect to time we call dA dt. Pi is a constant, so that just comes straight down. The derivative of r squared is 2r to the first, but now we have to take the derivative of r with respect to time. Okay, the task was how fast is the area increasing? This is a rate of change of area, so this is what we're looking for. How fast is the area increasing? We must be given enough information to just plug in the numbers. Let's see. We know that the rate of increase in radius is 3 centimeters per second. That's going to go here. The radius is changing at 3. Obviously, pi and 2 are just numbers. We need to know what r is, though. So read the problem carefully. At t is equal to 10 seconds, we should see r is equal to 30 centimeters, right? Because there's beginning. This is 1 second later with 3. This is 2 seconds later with 6. 3 seconds later with 9, right? 3 centimeters every second. Okay, so we plug all these numbers in, and we get the rate of change in area with respect to time is 2 times pi times 30 times 3. Okay? If we put the units in, it sort of confirms that we have the right idea. 2 and pi are unitless. The 30 came from here. That was the radius, 30 centimeters. The 3 came from up here. That was the rate of change of the radius, which was 3 centimeters per second. And then if you look at the units on the right-hand side here, it's pretty clear. We have, let's see, 3 times 2 is 6 times 30 is 180 pi centimeters squared per second, right? Centimeters times centimeters. And that is a rate of change in area over time. Okay, so that's a fairly straightforward related rate problem. Second problem. Now we have a triangle. This is a typical problem in calculus where there's a ladder leaning against the building. So we have this ladder, and to make it easy, we'll say this is a 13-foot ladder. It's not an extension ladder. It just stays 13 feet long the entire time. And let me see if I can move this ladder. Okay, so this particular ladder now can be moved. One of the things we want to have happen is we want to keep the ladder leaning against the building. So as the top of the ladder slides down the building, the bottom of the ladder, which is called the foot of the ladder, goes further and further away from the building. And so you sort of have to imagine the ladder sliding down the building like that. Okay? And again, sort of hard to do on the smartboard here. The ladder is leaning against the building like that, and then all of a sudden it starts to slide down the building. Okay. 13-foot ladder. Slides down DOWN building at a rate of, let's say, 1/2 of a foot per minute. How fast is the bottom of the ladder moving when it, being the bottom of the ladder, is 12 feet away? Okay. We start with our geometry equation. Let's call the horizontal distance x, the vertical distance y. These are changing with respect to time. The ladder is 13 feet long. That doesn't change. So here's our geometry equation. X squared plus y squared is 13 squared. Because x and y are both changing with respect to time, we can differentiate with respect to time. With respect to time. So we have 2x dx dt plus 2y dy dt, and the derivative of 13 is 0. Right? Derivative of a constant is 0. Okay, so this is our geometry equation we have to get from the setup. This is our rate equation that we get from differentiating with respect to time. We have to be given enough information to plug all these in. And let's see, what are we looking for? We're looking for how fast is the bottom of the ladder moving. Okay, so this is a rate, right? So we're looking for how x is changing. This is the rate at which the bottom of the ladder is moving. So that's what we need. We must have all the other pieces of information. Let's see. We need an x value. Well, I think they tell us that right here. X is 12, so we can put that in. So 2 times 12. We don't know dx dt. That's what we're looking for, so we'll leave that there. 2, do we know what y is? Well, basic geometry will tell us that if the bottom of the ladder is 12 feet away and it's a 13-foot ladder, this has got to be 5 feet. So y has got to be 5. 5, 12, 13, a nice Pythagorean triple. How fast is y changing? Okay, so go back to the problem again. It says a ladder slides down the building at a rate of 1/2 foot per minute. Now remember, y is this distance here along the side. And because the ladder is sliding down, y is decreasing. Y is decreasing so that the rate of change of y is a negative. So negative 1/2 foot per minute. Okay, and all that's got to equal 0. So at that point, we just go ahead and solve for dxdt. dxdt would be equal to, what's this, 5 divided by 24. The units here would correspond with the units of x and t. X is in feet, and t was in seconds, right? No, minutes. Okay, 1/2 foot per minute, so t is in minutes. Feet per minute. That's how fast the bottom of the ladder is moving when the bottom of the ladder is 12 feet away. Okay, let's see, how much time is that? That's 10 minutes. let me stop this. I may do another one tomorrow for you to look at tomorrow night prior to Friday's test.